So in this podcast I want to talk about circular motion. So I'm going to be considering a particle going around a circle of radius r, and it can be going this way or it could be going this way, and it could be starting here or somewhere else. So to start everything, let's just introduce some notation. So the position vector of a point on the circle is typically going to be described in terms of the unit vectors I and j, and it will have the form r, which is the radius of the circle, times the cosine of an angle, which I'm calling here theta, and I'm marking it here, times I, plus r, the radius, times the sine of theta times j. That's a typical description which we will generalize later on. But this is a static description. There is no mention of the point changing with time. So what I want to do now is to write down a description involving the time. And to do that, let's say that r as a function of time has the form r of t is the radius of the circle times the cosine of something which will depend upon t, and I'm going to call it omega t, I, plus r sine omega t, j. So this is going to be our starting description. I'm going to talk about what omega means. We know what r is, it's the radius of the circle. And we're going to talk about whether this is anti-clockwise or clockwise motion and how to go to the other format, and where the particle starts at t is 0 and how to describe it starting at other points. So on the next slide, let's look at this and see a bit more what it means. So this was our description on the previous slide. And what I want to do is first of all just to argue that the dependence on omega t here and here corresponds to a particle moving with a constant speed. So to understand that, let's look at the velocity, and the velocity vector as a function of time is the derivative with respect to time of the position vector. So we just have to differentiate this, and then we add to it the derivative of this, and I and j are constant unit vectors. So the derivative of cosine is minus sine, and we're going to pull out a factor of omega using the chain rule. So what we have is minus omega r sine omega t I, plus, and now differentiating the second term, it is omega r cos of omega t j. So this is the velocity, and what about the speed? Well, the speed is the norm of the velocity, so the speed v is given by the modulus of this vector. So to get that, all we do is we take this and square it, take this and square it, add the two of them together and take the square root of that sum. So we're going to get the square root of minus, when we square it, is going to become plus, so that sign will become plus, omega squared, r squared, and then sine squared. So it's omega squared, r squared, and in the next term, when we square this, we're going to get omega squared r squared as well, times cosine squared. So omega squared r squared is a common factor, so I might as well just open a bracket immediately, and we have sine squared from the first term of omega t plus the cosine squared of omega t, close the bracket and put all of this inside the square root. Now this is of course 1, sine squared plus cos squared is 1, so we have the square root of omega squared r squared. And if we assume that omega is positive and that r is positive, r being the radius of the circle, omega we're going to take by convention to be positive, then the square root of omega squared r squared is omega r. So therefore the speed is omega r, and this is constant. It does not depend upon the time. So this description here corresponds to motion with constant speed around a circle. Of course, the velocity is changing because the velocity does depend upon the time, but the speed, its modulus, does not. So that's good. What does omega itself mean? Well, let's think about the periodicity property of the trigonometric functions cosine and sine. So we just recall now that the cosine of some angle, let's call it phi, plus 2 pi, is the cosine of phi, and ditto for the sine function. So they have periodicity of 2 pi. So if here omega t is increased by 2 pi, the position and also the velocity of the particle will not change. So we see that the motion is periodic, so it's going around the circle with a period which I'm going to call capital T for the period, and the time is going to be such that omega t is equal to 2 pi. So whenever t goes to t plus something such that omega t is 2 pi, we have periodic motion. We've gone once around the circle. So this is going to correspond to the period being 2 pi over omega. So that's the periodicity, and that tells us what omega means, and we call omega is the angular frequency of this motion. So just to be a little bit more explicit about this, if I look now at the cosine, for example, we could do exactly the same for sine of omega brackets t plus the period capital T, what we get is the cosine of omega t plus omega 2 pi over omega, because that's what the period is, and omegas here cancel, so we can just cancel them, and we have the cosine of omega t plus 2 pi, and that is equal to the cosine of omega t because of the periodicity property of the cosine function, and exactly the same thing applies to the sine function. And omega itself, from this equation here, if we multiply both sides by omega and divide both sides by t, omega is 2 pi over t. So if t, capital T, the period is 1 second, it takes 1 second to go around the circle, then omega is 2 pi, so it goes through 2 pi radians in 1 second. If t was, say, 2 seconds, then omega is 2 pi over 2. That means omega is pi, and that corresponds to it going through pi. It would go around half of the circle in 1 second. After all, it takes 2 seconds to go around the circle. So this is our understanding of the angular frequency it's the number of radians that the particle goes through in its circular motion during 1 second. So let's look now at what this description of circular motion corresponds to in terms of the direction and the starting position, and we're going to argue how to generalize that, and that will be the end of the podcast. So on the previous slide we were looking at this description of circular motion going around a circle centered at the origin of radius r with angular frequency omega, and the velocity is obtained by differentiating the position vector with respect to time, and that gave us this result. So what does this correspond to in terms of the motion? So let's say that this is our unit vector I, this is our unit vector j, the direction, so this is the x direction, this is the y direction, and here is our circular motion, and this corresponds to being at position r0, and this would be the position 0r. R is the radius of the circle. So if we look at these equations here, what we see is at t is 0, so 0 seconds, r of 0 is, and we just go into here, and when t is 0 we have cos of 0, which is 1, so we have ri plus r, and the sine of 0 is 0, so the j component is 0. So it is r unit vector I. So that means at t is 0, our particle is starting here. So it's starting on the x-axis. And the velocity v of 0 is given by, look at this equation here, when t is 0 this vanishes, sine of 0 is 0, cosine of 0 is 1, so we have omega rj. So it's omega rj. So omega and r are both positive. R is the radius of the circle, it's clearly positive. Omega is the angular frequency, the number of radians that it goes through per second, that's positive as well. So omega and r are both positive, so v of 0 is in the j direction and it's positive, so that means at t is 0 our particle is moving straight upwards. So this corresponds to starting here, and the motion is anti-clockwise. So we have anti-clockwise motion starting on the x-axis. So what I want to do in the rest of the video is to discuss clockwise motion and starting at other points on the circle. And clockwise motion is very, very simple to understand. Imagine that you're looking at a film of motion of a particle going around the circle anti-clockwise. If you take that film and you play it backwards, you would be moving clockwise. So all we need to do to describe clockwise motion is to reverse the sign of t. So to describe clockwise motion, what we do is we let t goes to minus t. So we just change the direction of time, as it were. So that corresponds to r of t, but we're going to flip the sign, and the cosine is an even function, so there is no change here. The cosine of minus omega t is the same as the cosine of omega t. So it is r cos omega t I, but the sine function is odd. The sine of minus omega t is minus sine omega t. So we have here minus r sine omega t j. So this starts at exactly the same place. When t is 0, that vanishes. It's starting on the x-axis, it's starting here. But the velocity, and we can check this now, the velocity as a function of time is going to be the derivative of this here. So the derivative is unchanged here, but there is an additional minus sign here. So what we obtain is minus omega r sine of omega t I minus omega r cos of omega t j. And if we put in, as we did here, t is 0, the position, the starting point has not changed. This vanishes, but the velocity at time t is 0 is minus omega r times 1, so minus omega r j. So that means that it is parallel to this axis and negative. It's pointing down here, and that corresponds to clockwise motion. So changing the direction of motion is quite simple. It just corresponds to changing the sign of t and substituting it into this equation here. So with that, I just want to look now at starting at different positions, and we'll move on to the next slide. So as we've seen, this description corresponds to a particle starting here on the x-axis at t is 0 seconds, and it is moving in an anti-clockwise direction. And if we would like to start at a different position, so let's say that we want to start here or here or here, what we will do is we will generalize this, and we generalize it by adding an angle to the argument of the trigonometric function. So we have r of t is r of the cosine of omega t plus theta I plus r sine omega t plus theta j. And now at time t is 0, we have r cos theta I plus r sine theta j, and that corresponds to being at an angle theta measured in the anti-clockwise direction from the x-axis. So that corresponds, in terms of a picture, to being, say, here, where this is the angle theta at t is 0, and this is still anti-clockwise motion. So that's at t is 0 seconds. So that's fine, and if you wanted to be at some arbitrary point on the circle, this is the right way to write it. But if we're going to be starting, say, at here, then there are ways of rewriting the cosines and sines that are actually quite simple, and it's worth doing an example of that. So let's just see. So here is an example for us to look at. Let's consider a particle that's going to start on the y-axis. So we're going to say at t is 0 seconds, the position vector is going to be 0, so it's on the y-axis, and we're going to choose y to be r, and that means that it's above the x-axis here, not here. And we're also going to consider the motion to be anti-clockwise. If if we want to look at clockwise motion, we just then need to change the sign of t. So what we get from this is that r of t is going to be, so it's r cosine of omega t plus, so what should theta be? Well, we're starting here, so we've gone from here through to here, that's an angle of pi over 2. So it's cos of omega t plus pi over 2 I plus r sine of omega t plus pi over 2 j. So that's our position vector, and in principle we could leave it like this, but because pi over 2 is a special angle and the cosine of pi over 2 is 0 and the sine of pi over 2 is 1, it's possible to rewrite this rather simply. So you can do this either from your knowledge of what the cosine and sine graphs look like, or what you can do is you can use the composite angle formulae to rewrite this and this. So the cosine of omega t plus pi over 2 is the cosine of omega t times the cosine of pi over 2, which vanishes, minus the sine of omega t times the sine of pi over 2, which is 1. So what we're going to get is the minus sign, r sine omega t I, and then similarly here, sine of omega t plus pi over 2 is the sine of omega t times the cosine of pi over 2, which vanishes, plus the cosine of omega t times the sine of pi over 2, which is 1. So we're going to get overall the cosine of omega t. So we have plus r cos omega t j. And this is the position vector for a particle starting here moving anti-clockwise. Just to check that it's moving anti-clockwise, let's differentiate this, and the velocity is going to be minus omega r cos omega t I minus omega r sine omega t j, where we just used the chain rule. And now we see that at t is 0 seconds, r of 0 is, come back to here, sine of 0 is 0, the cosine of 0 is 1, so it's going to be r j, and the velocity at t is 0 seconds is going to be in a similar way. This vanishes because of the sine, this is 1, so it's minus omega r I, and that tells us that the direction of the motion is parallel to the I-axis, but it's pointing in this direction, so we're starting here, as you can see here, starting up here, and the motion is that way. It is indeed anti-clockwise. So this is our description of the position vector that fulfills this requirement. So I hope this has made some sense. On the next slide I'm going to write out a couple of questions for you to do, and on the final slide I will just write out the answer in this form. I hope this has been useful to you. So here are two exercises for you to work out. How would you describe circular motion such that at time t is 0 seconds the position vector of the particle is 0r and motion is clockwise? And secondly, the final exercise, at t is 0 seconds the position vector is minus r 0 and motion is anti-clockwise. And if you could work those out, what you will find is on the next slide you will get the answers written down, but without any details of how to get there. I hope that what we've discussed up to now will let you be able to do that. So I would pause and try and solve those problems now. So here are the solutions to the exercises, and I'm just going to explain to you how you could have essentially just written them down. So you know that it's going to involve a sine and a cosine, and you want at t is naught the value of x to be 0 here, so you want this to have a sign, so that will vanish. You want this to be positive, so it's going to be r cos omega t, not minus r cos omega t, that's set. And then what's the sign here? Should this be plus or minus? Well, when you differentiate this, you're going to get omega r cos omega t multiplied by I, and you want the motion at t is naught to be parallel to the I-axis, so you want this to be positive, so we need this to be positive. So we could essentially write that straight down. Similarly, if we look at this example, at t is naught, the position vector is minus r naught, so we want to be starting here. So we want minus r cos of omega t, so that at t is naught we have minus ri. So that bit is quite easy to write down. And the other term is going to involve a sign, so that the value of y is naught. It starts on this axis. And is it positive or negative? Well, when we differentiate it to obtain the velocity, we want the velocity to be parallel to this axis and to be negative. So we have a minus sign here, because when we differentiate this, we get minus omega r cos of omega t. So at t is naught, it's minus omega r times 1 times j, and that's correct, that's negative, and the derivative of this would vanish at t is naught. So we could actually really just write these answers down, but we can understand how this is true and how to get from one formula to another using the general methods we've discussed in this video.